Welcome friends to my YouTube channel. Now, yesterday's lecture I started to do few numericals, okay, and I started the chapter first law. That means from first law I did few numericals. Four numericals I did yesterday. So I hope that you all understand these numericals, and the numericals regarding first law are not so tough, very simple working formulas. Okay, so you can also practice these numericals from other books like Brijlal or say B Gupta, or you can say you can also get few problems on CL Aurora volume 2. Okay, so you can did it by taking numericals from different books. That will increase your concept. Okay, so in today's lecture I will going to do some numericals related to heat engine. So the first numerical is given that, okay, the first numerical that is given: find the efficiency of a Carnot engine. Find the efficiency of a Carnot engine working between steam and ice point. Okay, so this is the first numerical. So this is a pure numerical. This is simple, that you always know that the formula is 1 minus T2 upon T1. So here, what is the source temperature? That is the steam. Okay, so yes. Okay, so what is the steam temperature in Kelvin? You can add 273 with 100. So this is the steam temperature, that is 373 Kelvin. And what is 2? Basically ice point 0 degree Celsius. So this. Okay, so you can easily get the efficiency. So substitute 273 by 373, that means 100 by 373. And since the efficiency can be expressed in terms of percentage, so you can multiply it and write it as percent. Okay, so if you take the calculate it, what will be the result? Okay, the result will be this. Just do it in calculator or mobile. Okay, the efficiency is expressed in terms of percentage, so that's why I multiply here by 100%, and the result is 26.8%. Okay, so this is the first numerical, the efficiency of a Carnot engine working between the steam and ice point. And steam is 100 degrees Celsius, so there is 373 Kelvin, and ice is 0 degrees Celsius, that means 273 Kelvin. Okay, so let us move to the second numerical. Okay, let us move to the second numerical. The second numerical that is given, okay, the second, find the efficiency of a Carnot engine. Okay, that is, we have to find out the efficiency of a Carnot engine working between 127 degrees Celsius, that is 127 degrees Celsius, and T2 is also given 27 degrees Celsius. This is given. And also we have to find out how much heat is rejected. Okay, find how much heat is rejected. Okay, so what will be this? This is 400 Kelvin, and this is 300 Kelvin. Okay, so we can easily find out the efficiency 1 minus T2 by T1, that is 300 by 400. So this will be what? 1 by 4, or you can say in terms of percentage, that is 25%. Okay, So this is the efficiency. Now you have to find out the second thing, how much heat is rejected. Okay, how much heat is rejected. So we use this formula, that is W equals to Q1 minus Q2. Okay, we use this formula. Oh, another thing that is given, it absorbs 80 calorie heat. Sorry, it absorbs 80 calorie heat. So if it is not given, then it will not possible to find out Q2. Okay, so this is given. I forgot to see it. Okay, so now this is easy. So what my eta will be, W upon Q1. So what will be my W? My W will be eta Q1. Okay, so what will be eta? 1 by 4, and your Q1 is given 80, that is 20 calorie. So how much heat will be rejected from this formula? Q2 will be what? Q1 minus W. You know Q1 80 and you get W 20. So 60 calorie heat will be rejected. Okay. So there are two parts. T1 and T2 is given. So you can easily find out the efficiency. 1 by 4, that is 25%. And another thing is given, it absorbs 80 calorie heat. Okay, now we all know the formula, efficiency equals to W upon Q1. So what will be my W? Eta Q1. Eta is 1/4 and Q1 is given 80, so 20 calorie. Again we know the formula, W equals to Q1 minus Q2. So how much amount of heat is rejected? Q2, that's equal to Q1 minus W. So this is also a simple numerical. So simple working formulas, you have to remember this thing, formulas. Okay, so that's why I tell always that at first you write down the quantities that are given, so it will be easier to remember the working formula. Okay, so this is the second numerical. So let us move to third numerical. So dear guys, kindly take your pen and papers and start to note it. Okay, or you can also see how I can do it. Okay, no problem, it's your choice. Okay, so here given a Carnot engine whose temperature of the source is 400 Kelvin. Okay, so given that source temperature is given 400 Kelvin, fine, and takes 200 calorie of heat at the temperature. That means what? Q1, that is 200 calorie, and rejects 150 calorie heat to sink. That means this is given, this 150 calorie. We have to find out the temperature of the sink and also find out the efficiency. Okay, also we have to find out the efficiency and temperature of the sink. That means we have to find out T2 and we have to always find eta. So first we have to find T2. So what the formula for a reversible Carnot engine? I already told previously that for a reversible Carnot engine, 1 minus Q2 upon Q1 can be expressed in terms of 1 minus T2 by T1. That I did in Carnot cycle. Okay, by considering PV relations for a perfect gas during adiabatic processes. Okay, so this cancels, minus minus also cancels. So for reversible Carnot engine must be, so this is for reversible Carnot engine. Okay, so this is for reversible Carnot engine. So given, what are given? Q2 is given 150 and Q1 is what? 200, and here T1 is given, that is 400. So what will be my T2? My T2 will be 400 into 150 upon 200. So this is simply 300 Kelvin. Okay, so we find the steam temperature 300 Kelvin. Now we can easily calculate eta 1 minus T2 by T1. So what will be my T2? 300, and what will be T1? That is 400. That is 1/4, or you can say 25%. Okay. So this is the result. Okay. So this is the third numerical. All are given. We have to find out eta and T2. So this is the answer. Okay. So this type of formula. For higher secondary students, I tell one thing, that you will get few numericals in joint entrance examination by using these laws. Okay, these questions will come in joint entrance examination or IEEE examinations. Okay, so you will get this from thermodynamics, or you will also get how to find out the area of a Carnot cycle, where a particular diagram is given. I will do it for you for later. Okay, later I also solve that kind of problems. Okay, so you will get these problems in joint entrance or IEEE exams. Okay, so for higher secondary students. So this is the one numerical. So let's move towards another numerical. So here this is numerical number 4. Here given that a Carnot refrigerator takes heat from water at 0 degrees Celsius and discard it to room temperature at 27 Celsius. Okay, so here given T1, this given 300 Kelvin, and T2 is given 0 degree, that means 273 Kelvin. Okay, so how many calories of heat are discarded at the room? Okay, no. Here the question is, a Carnot refrigerator takes heat from water at 0 degrees Celsius and discard it to a room temperature at 27 degrees Celsius. 1 kg of water at 0 degrees Celsius to be changed into ice at 0 degrees Celsius. Okay, so remember 1 kg of water at 0 degrees Celsius is to be changed into ice at 0 degrees Celsius. Okay, so 1 kg of water at 0 degrees Celsius is to be changed into ice at 0 degrees Celsius. At 0 degrees Celsius. So what will be my Q1? Okay, we all know what is the latent heat in this case. 1 kg, that means 100 gram into 80 calorie per gram per degree Celsius. That's why I converted it to gram. Okay, so this is the say Q2. Okay, this is the Q2. How many calories of heat are discarded at the room? Obviously, fine. So this is the Q2. This is given Q2. Now what will be my Q1? If you put this relation Q1 by Q2 equal to T1 by T2, you can easily find out Q1. So this is T1 Q2 upon T2. So if you substitute 300 into 1000 into 80 by T2 is what? 273, and you will get this. Okay, the result will be this. I repeat the question. A Carnot refrigerator takes heat engine from water at 0 degrees Celsius, that means this T2, and discard it to a room temperature at 27 degree Celsius. That means room temperature is the source. 1 kg of water at 0 degrees Celsius is to be changed into ice. Okay, so how many calories of heat are discarded at the room? That means you have to find out the what amount of heat is given to the room, that is Q1, that is the source temperature. Okay, and here you have to realize the fact by from this that 1 kg of water at 0 degrees Celsius when converted into ice at same degree, then what will be the latent heat? We all know M into L, and what will be M? M is 1 kg, that means 1000 gram, and what will be L? 80 calorie per gram. Calorie per gram per degree Celsius. That's why I write it Q2. In this problem, this is the main thing that you have to understand. What will be the amount of heat drawn from sink? We all know the formula of latent heat, M into L. M is given 1 kg, that's 1000 gram, and what will be L? 80 calorie per gram per degree Celsius. So you have to understand this, and thereafter you can get the value of Q1 by knowing this formula. Okay, thank you. So this is the fourth. So I just do one numerical for today's lecture, and I will stop this lecture. Okay, just one numerical, one more. Just practice these numericals that I did. Okay, this is a interesting question. An inventor claims to have developed an engine working between 6000 Kelvin and 300 Kelvin. Okay, so inventor claims that he developed an engine working between 600 Kelvin and 300 Kelvin, capable of having efficiency 52%. Okay, capable of efficiency 52%. So question is comment on his claim. Good question. Comment on his claim. Okay. He said that he invented an engine which is working between these two temperature limits, and that engine has the capability of efficiency 52%. So at first you have to find out the efficiency. That is 1 minus T2 upon T1, 300 by 600, that is half, that is 50%. So we find out the efficiency of a reversible Carnot engine working between these two temperatures, which is found to be 50%. But he claims that his engine has the efficiency 52%. And from Carnot theorem, what we know? No engine is more efficient than the reversible engine. That means the maximum efficiency will be 50%. And he said that the efficiency is 52%. So this is not possible. So claim is invalid. The answer is claim is invalid. Okay. So dear guys, for today's lecture up to this. On my next lecture I also going to do again few numericals on my next class. Okay, so if you don't subscribe my channel, then kindly subscribe it. Thank you.